Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. I think we're going to explore how temperature and humidity can accelerate failure in a way that we can exploit for testing. Is that right?
Yep. And I'm drawing a blank on his first name, but Peck, P-E-C-K. And at one point he had a co-author when he kind of redid the work he was doing and came out with a slight modification to this equation. But it basically has a ratio of relative humidity from the field to in the test chamber, and has a exponent on it, which is, I think in the paper is like 2.66 or 2.7, somewhere in there. Mm-hmm. And then it has an Arrhenius part of it, e to the negative E activation energy divided by Boltzmann constant, and then some inverted ratios of temperatures in Kelvin, which I'm waving my hands going, if you want to see the equation, go look it up. It's easy to find. But the question is from Lokesh, is what is the relation of using a conservative RH constant, the exponent, as like 2.66, but use like 2.7 or 3 instead in the acceleration factor calculation, right? So you say, how about if I nudge that exponent up a little bit as an intention to be a little bit more conservative? That's one part of it. And is it somewhat related to an average activation energy of the device under test or the component under test? And I was like, the way I understand Peck's equation, and I have his paper, I've read the paper, it was a long time ago, it was in the late 60s, early 70s, if I remember right. He gathered a whole pile of studies of people that were doing epoxy enclosures for electronic components, for ICs essentially. And there was a whole bunch of, it was a new technology. Up until that point, transistors were in metal cans and would be sealed inside a metal can. And so somebody came up with the idea, well, why don't we just put some goop over it? And one of the issues was the goop, the epoxy, wouldn't bond to the lead frame. So think of it as the component that had 6 leads sticking out of the epoxy, and then you would solder those leads onto a circuit board. The little bugs looking things, like caterpillar type looking thing. And the issue that the temperature humidity testing found out was that if you don't get a good seal between that epoxy and the lead frame, if you add a little bit of temperature, a steady state temperature, and it's in a high humidity environment, it will create a failure due to corrosion of the active silicon. Because once it gets a little bit of this moisture and atmospheric contaminants into it, it fails pretty quick. And so they were testing the ability of this new fangled goopy stuff over the top of the silicon to actually make a good seal. And there were hundreds of tests run by all kinds of different vendors, and they were all being published all over the place. And so Peck and colleagues gathered up all of those things, laid out all the data on a great big regression analysis, and came up with this equation, which seemed to explain the results of all of these different tests. Now, it wasn't perfect. There's some variability. Some tests were done under different conditions and weird ways and had odd results, but he put in, I think it was like on the order of 200 different sets of data. And the equation was essentially just a empirically driven best fit line for this particular equation. And why that equation? Because it happened to explain the results. It wasn't anything fundamental or physics of failure derived or first principles, anything. It was, we got a pile of data, let's fit a line to it.
Right.
Right? I mean, is that I don't know if that makes any sense or not, but that's the way I understand it. It was just a regression practice to say, we got to average these things out.
So your understanding of Peck's derivation is a little bit more advanced than mine, but
Okay.
I remember some of the the details you're talking about sound familiar, but I think it's not necessarily a bad thing to use empirically fitted data, in my opinion. SN charts, for example, are classic examples of that.
Yeah.
Where you test huge amounts of new alloys to see how long it will take before they fatigue to failure. And because you have so much data, the empirical line of best fit is actually really, really robust.
Yeah. But it's one of those, back to the question was, well, what if I use a more conservative exponent? Well, you can. Why don't you take the results that you get and say it's going to, and if the results say your product's going to last 10 years and you're uncertain about it, cut it in half, give yourself a margin of error and say, well, we're good to 5 years. I've seen people use equations like that, saying, well, we know there's lots of variability, there's some uncertainty in this. And so we're just going to put a safety margin on it and say, well, the test says 10 years, we're going to claim 5. And we're still, and does that change our mind or not? But the issue is that, well, the parameters came from somewhere. So I would suggest go get, where did it come from? And that's what drove me to go find these papers and where did this number come from? And it turns out that it's a very specific failure mechanism for a very specific technology. And so it is what it is, right? If you can use that equation, the form of that equation, the ratio of relative humidities and the activation or the temperature through the Arrhenius fragment of it, and run your own set of tests and then fit a line to it. Determine your own parameters. Having thousands of data points would be helpful, but just assuming that it's something else is, I don't know if that's very useful.
Right, and I think we've talked about this on previous podcasts and webinars and things like that, is that if you're serious about accelerated live testing, when you take a model from a textbook like Peck's model, you have to confirm it for your scenario.
Yep.
It sounds to me like the question revolves around a desire to do a single or at least a small number of accelerated live tests at higher humidities and temperatures, have that singular point estimate at that singular set of elevated stresses and try and use a conservative number to get back to the real world to try and introduce margin. That's, I mean, I know what your recommendation is because I'm similar. You just can't do that. You have to confirm the model applies to your scenario.
Yeah. So run your tests and get enough failures that you get a plot of this line and compare it to the one that the equation says you're getting. Or estimate, if you do enough samples, you can get estimates of the parameters from your data. And are they within reason or close enough to what Peck came up with? And then you could use one or the other. But the fundamental problem I have, and this comes from lots of experience of seeing this equation in dozens of textbooks. And it says, oh, if you're doing temperature and humidity testing, use this equation. Here's the parameters. And I've seen it used on solar panels. I've seen it used on laminates. I've seen it used on fiberglass. I've seen it used on all kinds of different components that have nothing to do with epoxy and lead frames. I've seen it used on bearings. Just because you have a temperature humidity chamber doesn't mean you can use Peck's equation. Those parameters are very specific to a particular circumstance. Well, I get a number out of it. Okay, stop it.
That's the key, isn't it? I think someone just wants to ask how I want a number. I want an answer. Yes, the answer would be nice, but I'm happy with an answer.
Yeah.
Can I shortcut the process by doing this, and this? Now, and there are plenty of ways you can shortcut the process, but it comes back to the decision. Like, even if you use wild interpretations of that exponent, and all it's going to do is change your time to failure estimate from 100 to 1,000 years, then you know what? That's usually going to outlast the service life of whatever it is you're doing. So you're done. You don't need to do any more.
Right.
You need to focus on other things that are closer to the edge of failure. So that's how you can short circuit the process. But if your company's going to live or die by the profit margin associated with the warranty repairs to this particular failure mode because it's right on the edge of the warranty period, you can't do it. You can't just, we'll pick an exponent and be conservative and then send it the emoji of 2 thumbs up to the boss and off we go. That's a recipe for disaster.
Well, sometimes you get lucky. And that's the hard part, is sometimes the design team was focused on it. They knew that this was going to be an issue, so they put in a higher speed fan and they keep everything a little bit cooler so that the environmental temperature that this component will see is a bit lower, or they put in a heat spreader, or they do something else in the design process to mitigate the effects of the temperature and humidity on this particular failure mechanism, completely independent of whether it's this right equation for the right thing. And you go run the test and you are using Peck's equation, but it's not related to that failure mechanism at all. And you get an answer, and it could be wildly overestimating the reliability or vastly underestimating the reliability. And if either one of those answers is, ship it, it may be really bad information feeding into that decision. But what I found is that the focus, when a team says, oh, this might be an issue. We had a failure in temperature and humidity testing early on. Now we're going to do a follow-on study, and we pulled out this equation to go sort it out. A lot of times that focus alone creates changes, or has people motivated to create changes to mitigate it, to reduce the temperature, reduce the chance of humidity incursion, and so on. And the product just gets better anyway, independent of your testing.
That doesn't sound like luck. That just sounds like, we talk about this all the time. It's way more important to improve reliability than measure it. So if you know that humidity and temperature is going to ruin the day of your device one way or another, and if it's not cost prohibitive to install a fan and whatever else you need to do to reduce the temperature and reduce the prevalence of humidity, off you go. It's
probably less expensive than doing the testing.
Right. I mean, I was just teaching a FAMICA course this week to Australian students, so it means I teach it at night where I'm based out of, so a little bit bleary-eyed. But I make the point, I use that smart lock example, that all these wonderful corrective actions that FAMICA can come up with, or a fault tree analysis, or a just good engineering judgment.
Mm-hmm.
If it's embedded in the first design, that's borderline free, because they're usually minor characteristics of a design you're not changing because it's a first iteration. And so it's way more important to improve reliability than measure it. So I wouldn't classify your scenario as luck. I just classify that as just smart design. Well, all right, it could fail like this.
Yeah.
Can we do it? Anything about it? Yep.
But the thing to do about it is to make sure that the design team understands the risk. There's this temperature and humidity thing is a concern. It can create this, and this kinds of problems. Here's the failure analysis of what's failed already. Here's options to solve that. Is money better spent than figuring out an adjustment to a parameter for some equation out of a book or a previous paper? I think is to summarize what you're saying, Chris. The second part of his question was, is this related to the activation energy? And I'm drawing a complete blank of what's this form of this equation had the humidity segment, and then it had the temperature segment, and those are just multiplied together. And I know that there's another one that's in the number of books where it has 3 components. And I think even the Norris-Landsberg equation has a couple of components, and they're just multiplied together. They're kind of taking in different stress factors and how they impart, and they're assumed to be independent. Temperature and humidity are in Peck's equation, are assumed to be independent and their impact on the failure mechanism. They have their own exponents and their own way that they create the magnitude of change. Change humidity a little bit is that part of the equation describes that. But it always struck me as odd is why everybody assumes those things are independent when temperature and humidity are anything but dependent. They're about as not independent as you can get. If I'm at 80 degrees, whatever scale you want to be on, the ability for air to carry more moisture is different. 80% relative humidity at 80 degrees is a completely different amount of moisture per volume of air than it is when it's at 40 C, for example. Mm-hmm. And so why we use relative humidity in this kind of testing is ludicrous to me. One, it's easy for us to monitor and measure and everything else, but it's the moisture content that we're actually interesting. How much actual water vapor is there per unit space or whatever, and how much opportunity is there for this droplet to get in the wrong place, kind of thing.
I think it's not just that, though. I mean, the other way moisture ruins a day of metal alloys that corrode is because they, especially when they get into cracks, they create essentially mini batteries with different potential.
Oh yeah, they enable electrolytes, the contaminants, the ionic chemicals, the chlorines and borenes and the various charged particles. They need something to move in, and a little bit of moisture is a great conduit for them to move about and do their thing. And water by itself is a great solvent. And so it can free these components that would then move around and destroy things.
Well, that which brings us to the next point is that it's not, you got to understand how it's failing, because the ability for ions to move and essentially facilitate the chemical process, I would argue, doesn't relate to the activation energy questions seems to be focused on. Far from it. What it doesn't mean it's not going to speed up the reaction. And it's also down to the geometry of the surface and all sorts of other things. Smoother surfaces tend to corrode a little bit slower as a result. If you have like cracks where water can really easily get into, that's where corrosion ruins a day.
I'm going back to the chassis. I had a car that, it corroded right along the crack lane. Yeah.
Right. That's because of the water. So no, I don't. The technical answer to the question is I don't believe the moisture content affects the activation energy for corrosion. But yeah, there's so much more to this than just that I don't know.
Well, there's a handful of equations that I'm thinking of electromigration. If there's not a voltage gradient that's over a certain threshold, it's just not going to happen, right? If there's not a moisture or a vehicle for the metal particles to actually move on or move through, it's not going to happen. So there is, and if I think there's temperature and temperature just means it goes faster or not. If you put it at absolute zero, it won't happen either, but that's a bit difficult to create a product to do that all the time.
Challenging, yes.
Yeah. But there's part of understanding the failure mechanism is if you get rid of the moisture, then you don't have this problem with corrosion. If that's the nature of that failure mechanism you're worried about. If there's no moisture, then temperature and humidity testing is going to be irrelevant for your product. And if you're putting it in space and it's perfectly dry, I really wouldn't worry about moisture contamination.
No.
If you can get it in space dry, that's the trick, which we're pretty good at. But the idea is that I'm going to come back to the equation is do the due diligence of if you really do need to run an accelerated test and you know that you've got something that's related to temperature and humidity. If it happens to be epoxy encapsulant of ICs with a lead frame, then Peck's equation as is probably still not perfect, but it'll be close. But if you're doing a battery enclosure and you're doing a temperature humidity test and and I don't know what failure mechanism you're looking for, Peck's equation is probably as wrong as you can get, kind of thing. You might be lucky. It might work. But it's back to that, do your due diligence. If it's really, really important and you have to do the testing, confirm the equation. And you might be in a completely different structure of an equation. It might be more relevant for your particular failure mechanism. Oh, I'm still drawing a complete blank. I know I'm going to go look it up after we get done chatting here. There's a structure of an equation where you kind of stack up the different stresses that are being applied, and they're just multiplied together. And I've always wondered how strong of an assumption you have to make, or how clear the assumption has to be that these stress factors are independent. And then how do you evaluate that? But that's just me. I am always skeptical of these things.
Healthy skepticism is never bad. But all right, so what have we done? We've covered the facts. We really need to understand the question or decision better. We need to. What else?
Well, just messing with the exponents might be an enjoyable exercise, but it's definitely not. I don't recommend it unless you really have done enough testing to know that you're fitting your own line to it, not just adjusting it to make it conservative. I'd wait to the results. And if you are really uncertain, cut your results in half if it's time to failure type of information. Is one way to think about it. And if it changes your decision, then you know that you need to improve your ability to understand what's going on and use the appropriate equation or enough samples or whatever. But I had it on the tip of my tongue what the name of that structure of the equations are. But anyway, the way Peck's equation is structured is the humidity and the activation energy are independent. They're separate. There's a chemical reaction that occurs, and there's the impact of how much moisture you got, and they have separate ways they interact with your failure mechanism. That may or may not be true. So it's always worth checking and backing up and looking at this. So my response back to initially was, well, you need to, here's where you can find the original paper. If this applies to what you're doing, this might help you understand it a little more, that kind of thing. But any of these equations, even if it's a physics of failure model and it's for SAC 305 solder and you're using SAC 308, if that even exists, does it apply? Is it completely different? You need to ask those questions every single time if you're going to do the try to create a result that's meaningful. So anyway, so it goes. We got a couple of great questions. We're looking for your couple of great questions so we can, one, help you get an answer or a direction and get you some information, but two, so that we have another episode to talk about what's on your mind kind of thing. So head over to accendoreliability.com/go/SOR. And you can find a couple of ways to get in touch with us. Chris and I and the other hosts are available through LinkedIn or our About pages. And so we're looking forward to hearing from you and what's on your mind and what questions or comments you have. So keep them coming. We're getting close to, I think we're at 860 some episodes now. So will your question be number 1,000?
Jeez.
Yeah.
Needs to be a good one.
Well, yeah. Well, I don't know. We won't save it to be the good one, but ask a lot of questions. You improve your odds of being the 1,000th episode. Yeah. That's the way I think of it. So anyway, thanks, Chris. Well, I'll talk to you again soon, I'm sure.
It's always a pleasure.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation if you have a question or a topic that you think we should discuss in a future show. Please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.